to prove similarity. So just like we had shortcuts for triangle congruence, like our side, side angle, side, all of those theorems, we have a few for similarity that we can use as well. Before we get into that, let's factor some algebra skills. Let's factor these two polynomials. We're probably really rusty on this part. So earlier in the week, we took out GCFs. These two don't have GCFs.
Wait, hold on.
Okay, we can't take out any numbers or any variables. So we're going to find something else to do.
So I can't put 9y on the outside?
We can't put 9y on the outside because this 16 doesn't have a 9y in it. So we got to try something else. Does anyone remember what we do for two terms? There's only one thing we can do. You probably briefly mentioned it in Algebra 1. This is a sneak peek for Algebra 2. If you have two terms, and both of those terms are a perfect square, can someone tell me what a perfect square is? We can take the square root of it, and it's a nice, pretty number or variable, okay? So when we have two things that are perfect squares, meaning this thing is something squared and this piece is something squared, then we can factor it into what we call a difference of squares, where we take the square root of each piece. Does anyone know what the square root of a squared would be?
2.
Not 2. The 2's are really going to cancel. If we take a square root, remember for square roots, there's like a hidden 2 out here. These 2's are going to cancel. Okay? They're going to cancel. We're going to technically divide them, and they're going to cancel. So the square root of a squared is just a. What's the square root of b squared then? B. Okay, so we can factor this into a plus and minus b. Okay? So that's what we're going to attempt to do on this one. We're going to attempt it. So what we did over here is we took the square root of each piece. So let's take the square root of each piece right here. Let's handle the number first. What's the square root of 9?
3.
Good, very good. 3. Okay? And if the square root of a squared was a, what's the square root of y squared?
Y.
Y. Okay.
Yes, king.
So the square root of 9y squared is 3y. That's our first piece. That's going to be the first piece in our parentheses. What's the square root of 16? 4. So that's our second piece. So this can factor into those two square roots that we just got, added together and subtracted. So 3y plus 4 and 3y minus 4. We call this a difference of squares. If we remember, difference in math means subtraction. We are subtracting two perfect squares, a difference of squares. You'll talk more about it in Algebra 2, but that's kind of like a little sneak peek. Questions on any of that? We take the square root of each piece and put a plus and a minus in between. That's our final answer. That's it.
This next one looks kind of hard.
This one you talked about in Algebra 1 a little bit. Does anyone remember the X method?
Oh, no.
X method?
Back, please.
Yeah, we're bringing back the X method.
God.
We set up an X. Okay.
Oh my goodness, man. I
That's fine.
haven't done this since.
So we set up our X method when we have 3 terms. Does anyone remember what number goes on top?
The big one.
Not necessarily the big one, but the last one. The last number. I'll explain it in a second.
64.
I want you to put the 64 on top of your X.
And then plus is on top, minus is on bottom.
You're thinking about something else.
Oh.
I want you to put your middle number, the 16, on the bottom.
I think I'm thinking about something else.
here's what we need.
It's all right.
We need to think of two numbers that multiply to 64
Oh, yeah.
and add to 16.
8.
8 and
8.
8. 8 times 8 is 64. 8 plus 8 is 16. So we're going over this because we might have lost these skills a little bit from Algebra 1, but they're coming back. Does anyone remember what we do with these two numbers?
Add.
Kind of. We're going to put them with our variable in as a factor. So we're going to do m, because that's our variable. Is this positive or negative 8? Positive. So we're going to add 8.
Oh my goodness.
So we looked at our three terms, and we tried to think of two numbers that multiply to our last constant term and add to the middle term. Once we have those two numbers, we just stick them next to a variable with a plus or a minus and some parentheses. We talked about this in Algebra 1, but this is coming back in Algebra 2. Also, since these numbers are the same, this is like m plus 8 times itself. So I could also write this as m plus 8 squared. M plus 8 times m plus 8 is m plus 8 squared. You have two of them, and we're multiplying.
Oh, we don't do the square.
Which also means I could call this something called a perfect square trinomial. Perfect square because it's equal to something squared. What about trinomial? Does anyone know what that means?
3 numbers.
3, very close. 3 terms. 1, 2, 3. Very good. So perfect square because it's equal to something squared. And trinomial because there's 3 terms. That's all from Algebra 1, hopefully. Questions on that? Okay, we're going to look at an application online, like we've been doing, that relates to this picture. So I'm going to pull it up. We're just going to do it as a class, but it's also in your notes packet.
Why don't we do those morning games?
We will after the lesson. We'll do a game. I want us to do a different game. I don't know what, though. I've been thinking. Okay, we're going to look at these two triangles. What I have done is set these two triangles up so that the only thing that's locked in as the same is the green angle and the red angle. So if I change the green angle on this triangle, the green angle over here is going to change. And if I change the red angle over here, the red angle over here is going to change. Right now, these triangles are set up to be similar because all of their ratios of their corresponding sides are equal. They're all 1.8. Let's see what happens when I change one of my angles. Let's change the green one. Let's make it bigger. If we notice, my triangles change a little bit. That angle gets bigger. But what happened to those ratios? Did they change? These fractions, did they change at all? They're the same number. And they're all still equal. So are these triangles still similar? Since my ratios are equal?
Yeah.
They're still similar, okay? So all we needed was these two angles to be the same. And everything else kind of just lined up. The similarity came from that. We could do the same thing with the red angle. We can make it bigger or smaller. And if you look, these fractions changed because I just changed the actual size, but they're all still equal. So all we need to figure out if two triangles are similar, all we need to find out is if they have two equal angles. Okay? So that's going to be one of our shortcuts for similarity. We don't need to always do the corresponding sides and do our fractions. We only need two congruent angles. Okay, so in your notes, what we noticed is that the ratios did not change. So the ratios of the corresponding sides were equal, meaning the sides were proportional. That's the word that we use. Highlighting that because it may or may not show up on your test, proportional. And they did not change when we made our angles bigger or smaller, meaning our sides were still proportional as long as those two angles matched. So, how many angles do we need to be congruent to determine if two triangles are similar? How many angles did we have locked in on there? We had the green that always matched and the red that always matched. How many is that? 2. We only need 2 angles to determine if two triangles are similar. Okay? So if we wrote a conjecture, that's our educated guess from Unit 1, we can say that if 2 angles of one triangle are congruent, they're the same, they're equal, to 2 angles of another triangle, so that's what we had up here. Our green angles matched and our red angles matched. That's our 2 angles. And what we found was that the triangles were similar. So then the triangles are similar. And this is our symbol for similarity. It's just the squiggle. Okay? So, when you're asked to figure out if 2 triangles are similar, all you need to find is 2 angles that match. 2 from each triangle that match with the other one. Questions so far? Because before we needed all 3 angles to match and all of our sides proportional. Now I'm saying here's a shortcut. We just need 2 angles to match. We don't even have to check the sides. So that's our first shortcut theorem, angle similarity theorem. Okay. We also only need 2, because if 2 angles are the same as the other 2 angles, we had a theorem last unit, the third angles theorem. That third angle is guaranteed to also be the same. So if we have 2, we really have 3. But angle similarity tells us that if 2 angles of one triangle are congruent to 2 angles of another, then the triangles are similar. So here we have angle A from the blue triangle is congruent to what? What's A congruent to? D. Okay, so that's one of our angle pairs. Angle A congruent to angle D. And we have angle B congruent to what? E. And that's all we need, are 2 angles. And our triangles are guaranteed to be similar. They're the same shape, they're just different sizes. So if that happens, then triangle ABC is similar to the other triangle, and our job is just to match our points. So what point went with A? D, what went with B? E, and then C and F went together. So D, E, F. So if you're asked if 2 triangles are similar, you're checking for 2 angles that are the same. Let's do that for this example. Again, we're just saying, are 2 angles congruent? This is a pretty hefty one. You'll get through the rest of this packet, so 3 pages total.
Gosh dang it.
I know, it's a long one. Okay, so we're going to look at each of these pictures and see if we have two angles that are the same. Let's look at this first one. Does anyone see right off the bat two angles that are the same?
Yes.
Which ones?
The right angle.
The right angles. Okay, so that's one angle. We have angle D, congruent to angle G.
Oh.
Okay. The other numbers that were given for our angles aren't the same. We have 64 and we have 26. Those aren't the same. However, we have two unknown angles. How do I find this one, for example, from last unit? We do math, but what kind of math? What do all of these angles have to add to?
90.
180. Okay, so I can take 180 and I can subtract off my 26. And I can subtract off, what's the measure of this pink one? 90, so I can get rid of the 90. And what's left is going to give me angle E, the one that I don't know. 180 minus 26 minus 90, that gives you 64 degrees.
Doesn't that mean the other one is good? Right.
Yeah, so now Hunter's saying, well, now I have two angles. These two are both 64. I know that angle E is congruent to angle H. So, back to our original question, are two angles congruent? We have one, we have two. So yes, they are. So we can say that these triangles are similar. And the theorem we use is the angle-angle similarity theorem. Remember our letters, A stands for angle, so this means we have at least two congruent angles. So let's write a similarity statement now. Let's do triangle CDE. So C was the 26-degree angle. What's the 26 or the non-highlighted angle over here? K. Okay, so C goes with K. What does D go with? That's the pink one. G. So then E goes with H. So triangle KGH. Questions on that one? There's going to be a section on your test just like last time that has a few pictures like this. And it's like, are the triangles similar? Yes or no? Which theorem? And then write the similarity statement. So these are going to be useful for you on a cheat sheet maybe. Let's look at the next one. The two triangles that we're looking at here are this small one at like the top, RST, and RUV. So the big one and the small one. I'm going to kind of draw the big one just like off to the side so maybe they're not overlapping and we can just see it a little better. So I'm going to draw a triangle RUV over here. Here's RUV. And it tells me that angle U is 48 degrees. So there's my 48. So now I'm really comparing this triangle that I just drew and this one at the top. Right off the bat, what angle looks the same? What number's the same?
U, 48.
Yeah, U and S, 48. So angle U is congruent to angle S. And now I'm looking for one more angle. I only have one number, so I'm not ever going to be able to find the other two numbers. So is there a way to say that angle V is the same as angle T? We don't have any more numbers to work with, so there's no way that we can say that piece. However, the other angle is angle R up here and angle R right here? Is angle R equal to angle R? Yeah, angle R is the same as itself. What property does that use? Reflexive, very good. So if we were writing a proof, we would say angle R congruent to angle R, and that would be our second angle. So that was one of those like hidden things from last unit, when they share an angle. These two triangles both share this top angle. So now back to our original question, are the triangles similar? Meaning, do we have two angles that are congruent? Yes or no? Yeah, Lola says yeah, we just found two angles. So we used the angle-angle similarity postulate. And now we just have to write our statement. So let's start with the small one, RST for the small one. Okay, what did R go with? What's pink? Yeah, R. Okay, S was yellow, that went with U. And then T and V were both left blank. So R-U-V. Questions on that one? We found two angles that were the same, so our triangles are congruent. Let's do the next one right off the bat. What two angles are the same? Which two angles are the same for the triangle on the left and the right?
None?
What's the measure of this pink angle? 90. What's the measure of this other angle? 90. So those pink ones are the same. Okay, so angle PQR, that's the one on the left, is congruent to PRS, the one on the right. So that's one of our angles that are congruent. We need to find another one, hopefully. The 50 and the 45 are not the same, so those are not going to help me at all. Let's find the missing angle. How would I find this top angle right here on my left triangle? What do all of those add up to? 180. So I'm going to take 180 minus 50 minus 90. And I'm going to get this angle at the top. If I do this, I would end up getting 40 degrees. So this angle right here is 40 degrees. Is there any angle in my other triangle that's 40 degrees? No, I'm shown 45, but 45 doesn't match either of these. So this one's not going to match either. So do I have two angles that are congruent? No, I only have one. So my answer here is that my triangles are not similar because I'm missing angles. I only have one, not two. Questions on that one? Okay. Next example is a little word problem. It says we have a hockey player who's passing the puck to a teammate by bouncing it off of this wall, and then it's going to the teammate. According to physics, the angles that the path of the puck makes with the wall, so this angle right here and this angle right here, are congruent. So let's mark those first. Here's the angles that the puck makes with the wall. And they are congruent. So those are my pink angles. The question is, how far from the wall will the teammate pick up the pass? Before we do anything, we have to figure out if we have similar triangles here. Okay? I have one angle already highlighted. I need one more. Does anyone see a congruent angle from here to here?
A and B.
Yeah, E and B, my two right angles. So my triangles are similar. ABC is similar to DEC by the angle-angle theorem, because we had two congruent angles. And now we can do stuff that we did on Wednesday, where we matched up our sides and we set up a proportion. So we set up a fraction equal to a fraction. We found where our variable was. Our variable's right here. It's x. So let's put x in there. And x is on the side DE. So that's the first two spots in our similarity statement. What other two letters are the first two spots over here?
AB.
AB. So DE corresponds with AB. So I'm going to put x over the 25. We're going to set up that ratio. So that's step one. Find your variable, put it over its corresponding side. So that's your x and your 25. We now have to find another pair of corresponding sides that's going to help us, that we can set this equal to. So over here, I have CE is 28 feet. What segment in my other triangle goes with CE? It's the last two letters.
BC.
BC. So this segment. So I'm going to put that ratio on top of one another. CE over BC. Which one should go on top? The 28 or the 40?
40. 28.
Over here, the x is on top, and the x came from my triangle on the right. So my triangle on the right has to stay on top. So I'm going to put this 28 on top. 28 on top of the 40. And now we solve for x. What method do I use to solve for x? It starts with a B. It's an insect. No, butterfly method. Butterfly method. Let's multiply these two. 28 times 50, not 50, 28 times 25 is 700, if you put that into a calculator. And then if we do our other part, x times 40 is 40x. Now I'm just solving for x. What's my last step here? Division. Divide by 40. We get x is equal to, if you put it into the calculator, 17 and a half.
Wait, divide by 40 for the whole thing? Or
Each side. It doesn't matter how you write it. It's all the same thing. But yeah, I couldn't do it like this. But we get 17 and a half. What am I missing for my answer? I don't want to just put 17 and a half. We have a word problem. I can be a little bit more specific. 17 and a half what? What are my units here?
feet.
Feet. So that's my final answer, 17 and a half feet. Questions on that one? Okay, you guys have made it halfway through. We're almost done. This one, write a similarity statement for the triangles. So anytime you see similarity statement, and as I was grading the learning checks, this is something that I noticed. So if you see similarity statement, that means you're writing triangle blank similar to triangle blank. That's what a similarity statement is. Okay, so this is what your answer should look like. So both of these triangles are going to be similar. We just have to figure out why, and then write the statement and find the variable, just like what we did last time. So first, I'm looking for congruent angles. What's angle A congruent to?
Angle D.
Angle D. So A goes with D. I'm just going to start setting up my similarity statement. A goes with D. So they're both listed first. Angle B is congruent to what? Angle E. So B and E can be listed second. And then my last one, C and F. So triangle ABC is similar to triangle DEF. That's my similarity statement. And then it says find the value of the variables. So I'm going to find where my variable is first. My variable y is right here. It's on EF. What does EF correspond with? So my last two spots over here. What are my last two spots over here? BC. So y is going to go with that 15 for BC. Those two are corresponding sides. Now I need to find another side length that's going to help me when I use the butterfly method. So the only other number I see is by 3 over here. That's for DE. Needs to go on top because it's from the same triangle that Y was from. And then this 3 goes with 5. So I'm going to put it over 5. That's the stuff that we did yesterday. I solve with butterfly method. So 5 times y is 5y. And 3 times 15 is 45. Last step, divide by 5. We get y is equal to 9. Questions on that one? We determined that the triangles were similar by AA. We set up our ratios and we used the butterfly method to solve. Same thing for the next one. Let's first see if we have angle-angle similarity. What's one angle that's congruent in each triangle? D and C. Okay, so that's one step. D is going to go with C. So I can list those two letters first. And that's the only number or congruent symbol that I have for angles. So that means I have a hidden one somewhere. So I'm looking for shared angles, vertical angles, or parallel lines. Does anyone see any of those 3 right here? What do you guys see? Vertical angles. Yeah, we have vertical angles right here. Those 2 angles are the same. Angle ABD and CBE. So we do have angle-angle. And we can say that triangle ABD, or if we change it, DBA, is similar to, well, D went with C, like we already said. B, from this triangle that's yellow, goes to B from my small triangle. So B. And then my last letter is E. So DBA and CBE by the angle-angle similarity theorem. Then we solve for our variable by setting up our fraction equal to a fraction. Find out where your variable is first. My variable's right here on CE. CE is in my first and last spot. What segment over here goes with CE? In my first and last? Yeah, DA. So this Z is going to go with 6. So these 2 pieces correspond. And now I just need one other piece of information of 2 corresponding sides that I can set these equal to. Well, on the right, I see a 6. That's BE. It's my last 2 pieces over here. And it goes with the 12, the BA. which one should go on top, the 6 or the 12?
6.
6, because it came from the same triangle that Z came from. So 6 on top, 12 on the bottom. We cross multiply, we use the butterfly method. 6 times 6 is 36. And then Z times 12 is 12Z. Last piece, divide by 12, you get Z is equal to 3. Questions on those ones? Okay, so that's angle, angle. You only need 2 angles to determine if 2 triangles are similar. We have another one that we're going to talk about today, and it is side, 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 which means we're going to need 3 sides to determine if 2 triangles are similar. So, on here, and this is posted to Schoology if you ever want to look at it after, but I have set this up so that the side ratios, all 3 have to match. So all 3 ratios are all going to be the same. Our scale factor is going to work, okay? No matter what, if I make them bigger or smaller, all the ratios are going to be the same. Let's look at what happens to the angle measure. Let's make sure that these triangles are similar. Because right now we only have 3 sides. I know nothing about my angles. So let's look. If I measure my angles, what do we notice about all 3 angles of each triangle? Are they the same or different? They should be the same. 66 and 66, 51 and 51, 63 and 63. So those 3 sides, no matter how big or small they were, if all those ratios were the same, it guaranteed my angles to be the same. No matter what. We can make it smaller, my angles are still the same. We can make it bigger, my angles are still the same. So now, as long as we have 3 corresponding sides that are proportional, we have similar triangles. So, if we fill this out, we noticed that the corresponding sides were equal. The ratios were equal. That's how it was set up. I guaranteed that all of these ratios were locked in. They matched. We measured the angles and we noticed that the angles were congruent. Corresponding angles were congruent. And then since we had all 3 corresponding side ratios and all 3 corresponding angles, the triangles were similar. And now, all we need is 3 proportional sides. So AA, we care about 2 angles. This one's going to be side, 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 where I don't care about the angles anymore. Yeah, I don't care about the angles anymore. I just care about my sides. Okay, so this is our side, side, side similarity theorem. If we have 3 sides that are, that the ratios are equal to 3 sides of the other triangle, then the triangles are similar. So, if the corresponding side lengths of 2 triangles are proportional, then the triangles are similar. So let's set up what we would need to know for this picture to determine that these triangles are similar. We would need AB to be matched with RS as a ratio, so as a fraction. We would need that to be equal to one of my other sides, BC, to be matched with ST. Those fractions have to work. They have to be the same. And they also have to be the same as our third side. We need all three. So I also need AC, which corresponds to RT. I need that fraction to be equal. So this is what you need. 3 different ratios, all equal. The top should all come from the same triangle. The bottom should all come from the same triangle. If you have that, then you can say that your triangles are similar. So ABC similar to RST. So we're checking for 3 sides now. So let's look at this first example. It says, is DEF or GHJ similar to ABC? So we're checking both of these triangles on the right with ABC. So let's set up our corresponding sides first. I'm going to start with the smallest, okay? And I'm going to color code. So let's have this be a yellow triangle, this be purple, and ABC be green. Okay. Let's match small to small first. And I'm only doing green with one of these. So let's do yellow first. Green and yellow. What's the smallest side for green? 6. Okay. What's the smallest side for yellow? 4. If we reduce 6 over 4, what do we get?
6.
What could 6 and 4 both be divided by? 2. If I divide them by 2, I would get the fraction 3/2. So that represented my green AB over my yellow ED, or DE. So that was AB over DE. Green on top, yellow on bottom. I'm going to do that for the other 2 sides of green and yellow, see if it gets us 3/2. So let's go to the medium size side. Let's do a 9. This is the medium size over here is 9. Well, yeah, over here the medium size is 6. What can 9 and 6 both be divided by? 3. And we would again get 3/2. And that represented the ratio from BC to EF. So BC over EF. Last one we need to check is the biggest side. That's AC over FD. So my biggest side over here is 12. Over here it's 8. So I'm going to put those in a ratio. What can 12 and 8 both be divided by? 4. And I would get 3 over 2 again. So, are my corresponding sides for these 2 triangles proportional? Yeah, all those ratios were equal. So my answer here is going to be yes. Triangle ABC is similar to DEF. Again, just paying attention to the ordering. AC went with DF. And they all have to be ordered the same. And the theorem that I used, well, I had 1, 2, 3 pairs of corresponding sides that were proportional. So this is side, side, side. 3 sides. Questions on that one? Okay, now we're going to check green and purple. So again, for the green, AB is my smallest side, and it's 6. And over here, my smallest is GH, and it's also 6. I divide those, I get 1. I go to my medium side, hoping that that 1 is my ratio. So my medium side over here was BC, it was 9. And my medium side over here is HJ, it's 10. Is 9 over 10 equal to 1? Are those the same? No, they're not equal. So I don't even have one pair of corresponding proportional sides. I have 0. Okay? So here, my answer is no. My triangles are not similar. Okay? I knew nothing about my angles and my sides didn't work out how I wanted. Questions on that one? All right, 2 more, and then we're done. This one says, find the value of x that makes these 2 triangles similar. Okay, we're going to line up the things that we need to line up. Let's look at AB. I'm just going to write all of my sides for one of my triangles first. So I'm going to write everything for AB on the top. AB, BC, and CA. Those are all 3 of my sides. I'm going to use my statement to match my sides. So AB has to go with DE, the first 2 spots. BC is in the last 2 spots. That has to go with EF. And then CA is the last and the first. That has to go with FD. So this is what we call from yesterday or from Wednesday our statement of proportionality. Let's set up some of these with our variable. So AB over DE is 4 over 12. And that has to be equal to BC is x minus 1, and EF is 18. So x minus 1 over 18. And I'm going to pause it there because I have enough to solve this. What method do I use to solve this? Butterfly. So 12 times x minus 1. You have to be extra careful here. You have to put that x minus 1 in parentheses, and we're going to distribute it. Okay? And then 18 times 4 is 72. I'm going to distribute my right or my left side. I get 12x minus 12. Now what should I do to solve for x?
12.
Add 12. I get 12x is equal to 84. I divide by 12, and I get x is equal to 7. We also could have solved this using this fraction, CA over FD. Well, CA was 8. FD was 3 times x plus 1. And that's also equal to either this one, which has some x's in, and I don't want to mess with double x's. So it's also equal to this one, my 4 over 12. So we could have also solved it this way, and we also would have gotten x equals 7. Questions on that one? Did we do this last one in the notes from yesterday?
No.
We didn't finish it? Let's finish this one, and then I'll save the last one from the notes today for tomorrow or for Monday, whatever day I see you. So let's flip to, this is on page 6 from last time, page 6. We never got through this one, and I wanted to brush up on something I talked about yesterday. So, yesterday we talked about just straight up similarity statements. One thing that we talked about was our scale factor. And I told you how to write these, and I mixed it up a little bit. When we write scale factor, I want you to always put the new shape on top of the old shape. So if it's the scale factor from A to B, B is my new shape, and it needs to go on top. Okay, so the second one listed usually goes on top. This only matters when it says find the scale factor. If you're just finding unknown variables, you can mix them up whichever way, it doesn't matter. But if it says find the scale factor, this is what I want you to do, new over old. Which also means if we're getting bigger, if our shape is getting bigger, our scale factor should be big. To go from a small thing to a big thing, we need to multiply by something big. It should be bigger than 1. We need to get bigger. And if our shape is getting smaller, our scale factor is less than 1. It's a fraction. We get smaller. Okay? So we're going to kind of use that to see if these two polygons are similar. Let's act like they are similar and we're trying to find a scale factor. So let's look at all of our corresponding sides, starting from the smallest. And let's go this way. So blue to red, are we getting bigger or smaller? We're getting smaller. So our scale factor should be small. It should be a small fraction. So we're getting smaller. Okay, so I'm going to put red, my new thing, over blue, my old thing. So this is new and this is old. So the smallest size from my new is RQ. What's the smallest size from my old? CD, 6. Four over 6, I reduce. What do I get?
2 over 3.
2 over 3, perfect. So to know that these shapes are similar, I need all of the other sides to have this same ratio, 2/3. So let's look at the next biggest size. Over here on the red, it's 6. What's my next biggest size for the blue? It's 9. I have both of those 9s there, so the 6 has to go with the 9 if this is going to work. I reduce that, and I also get 2/3. And then I jump to my biggest sides. That's my KL, that's 8, and BA, that's 12. So 8 over 12. I divide both of those by 4. I get 2/3. So are my corresponding sides proportional? Yes. So corresponding sides proportional. But can I determine that these two polygons are similar? They're not triangles, so I can't use AA or SSS. Do I know that these things are similar? Technically, I don't, because we only have one angle. So we don't know if all corresponding angles are congruent. That's the piece that we're missing. We checked off the sides with our scale factor 2/3, but we don't know if our angles are congruent, so we're not sure. So this one we don't know if they're similar. Main thing that I wanted to talk about though was the new over old. Questions on anything from today?